In today's brief, we're completely deconstructing an engineering marvel that honestly, you probably walk past every single day, but never give a second thought to. Most of us, we think of aluminum foil as just that simple stuff we use in the kitchen. But today, we're totally shattering that perception. We're going to break down the industrial uses of foil, its microscopic design, and those 5 field techniques containing engineering secrets that professionals use to make sure it holds up under extreme stress. So if you're ready, let's uncover the engineering secrets hiding right in plain sight.
Now, I want you to just think about this for a second. What exactly holds together those massive industrial systems, the ones exposed to extreme temperatures, crazy high pressure, and just brutal weather conditions? Is it welding? Maybe heavy steel bolts? Well, yeah, those definitely form the skeleton, sure, but the true hero here, the actual lifeblood that keeps the heat, air, and vapor exactly where they need to be, is typically industrial foil tape. And hey, do not think of this as the flimsy tape sitting in your junk drawer at home. No way. This is a heavy-duty, precisely engineered vapor and thermal barrier. It's literally a razor-thin armor that allows billion-dollar industrial facilities to breathe and actually survive.
Now, what's really interesting here is the striking visual difference between these two materials. On one side, we've got the standard aluminum foil tape series from Hike Trade. It's got this flawless, perfectly smooth surface. I mean, it reflects light almost like a mirror. But then you look at the other side, and things change completely. Instead of that smooth finish, you see this distinct grid-like square structure. This is the cross-woven, scrim-reinforced version. And honestly, just by looking at it, you can instantly tell that this reinforced tape is built to take on some seriously harsh conditions.
So what's the actual engineering behind this visual difference? Well, standard foil tape gives you that essential baseline protection, right? It reflects heat and light, it's an absolutely excellent vapor barrier, and it's highly flame resistant. Plus, it has this crazy powerful adhesive to stop air leaks in their tracks. But when you step into the intense world of heavy-duty HVAC, heating, ventilation, and air conditioning, the rules of the game completely change. That's exactly where the reinforced foil tape steps up. That grid structure we just talked about, which is technically called a scrim, gives the tape massive tensile strength. The big takeaway here? Standard tape guarantees a perfect seal, but that reinforced scrim guarantees the seal won't rip or blow out under massive physical stress in brutal industrial environments.
Of course, for these engineering marvels to actually do their job in the field, they have to come in the right sizes. The dimensions are totally standardized around the real-world challenges professionals face every day. For widths, you're looking at 50 millimeters, 75 millimeters, and for those really wide surface areas, 100 millimeters. As for length, it rolls out to the job site in 25-meter and 50-meter increments. And look, these aren't just random logistical details. They give crews a totally practical foundation to efficiently cover everything from really tight pipe curves to massive, sprawling ventilation ducts, all while keeping the number of seams to an absolute minimum.
Okay, let's really dive into this. Up until now, we've been talking about visible surfaces and lengths measured in meters, but the actual battle for these tapes, that's won or lost at the microscopic level. We're talking about microns, literally thousandths of a millimeter. It is absolutely fascinating to realize that a difference of just a handful of microns in thickness is exactly what dictates whether a critical system survives freezing and cracking in the dead of winter or melting down under extreme industrial heat.
These technical specs, they actually tell a pretty incredible story of endurance. So the baseline 18-micron tape can handle a very respectable -20 up to +80 degrees Celsius. But as the industrial demands go up, so does the thickness. If you step up to just 30 microns, suddenly the heat resistance shoots way up to 120 degrees. And if you're dealing with systems out there in punishing polar light conditions, we're talking -35 degrees, you absolutely have to upgrade to the 40 or 50 micron tapes. These specific thicknesses hold the entire system's integrity together against massive temperature swings. Meanwhile, that reinforced tape we talked about earlier, it maintains its sheer, brute physical strength right between -30 and +80 degrees. It's crazy to think about, but these microscopic variations, which are literally thinner than a single human hair, are the exact things stopping billion-dollar facilities from just falling apart.
All right, let's move forward and see how this all actually builds in practice. Because look, all of these technical data points, the tensile strengths, those crazy -35-degree micro tolerances, they might look absolutely fantastic on paper in a lab. But where do these extreme engineered limits actually get put to the test in the real world? Where exactly can we find this invisible armor hard at work inside the massive structures that we literally surround ourselves with every single day?
Well, this list right here is essentially a blueprint of our modern infrastructure. Right at the top, you've got HVAC duct sealing. If there's even the tiniest little air leak in those channels, the energy efficiency of the entire building just plummets. Following closely behind that, we have air conditioning systems, thermal insulation, and pipe insulation. Out there in the field, these tapes are actively preventing heat loss around pipes that carry scalding hot water, or on the flip side, freezing refrigerant gases. Ventilation systems, general industrial, and construction applications totally rely on this stuff too. From those towering city skyscrapers to massive sprawling factory floors, these materials are working relentlessly. They're a critical component keeping the engineered, comfortable climate securely locked inside and the chaos of the outside world firmly outside where it belongs.
But hold on, we have to stop right here for a second. Because just holding a roll of 50-micron tape that's engineered to survive 120 degrees Celsius, that doesn't actually guarantee it's going to do its job flawlessly. Material science means absolutely nothing without proper application. To actually guarantee adhesion, professionals rely on 5 specific field techniques containing some serious engineering secrets. Because honestly, a poorly executed prep job can throw all of that expensive lab-tested engineering straight into the trash in a matter of seconds.
Okay, so here are those 5 fundamental field secrets for guaranteed success. Step 1. Surface preparation. You cannot just wipe a pipe and stick the tape on. The surface has to be perfectly clean, completely dry, and entirely free from grease, oil, or even just dust. If it's not, that powerhouse adhesive is going to bind to microscopic dust particles instead of the metal, and it will ultimately fail. Step 2 is application pressure. The pros don't just use their thumbs, they use a squeegee to firmly press out any air bubbles and mechanically activate the pressure-sensitive adhesive. Step 3, you've got temperature thresholds. You actually have to apply the tape when the ambient room temperatures are within a specific operational range to ensure it gets that immediate tack. Step 4 is tension control. If you stretch the tape too much while you're applying it, you risk completely compromising the vapor barrier. And finally, Step 5, the storage secret. You can't just toss these rolls into the back of a hot work truck. They need to be stored vertically in a climate-controlled room sitting right around 20 degrees Celsius and 50% humidity, and you have to use them within their 24-month shelf life. If you miss even one of these 5 steps, your extreme temperature tape is going to fail before you even unroll it.
So it turns out engineering isn't just something that gets manufactured in a factory somewhere. It's a discipline that has to be actively applied in the field with the right knowledge. The next time you look up at a massive commercial building, a huge mall, or a modern hospital, I want you to keep this in mind. That perfect internal climate, the comfortable air, the stellar energy efficiency, they aren't just held together by heavy concrete or steel. They are actually held together deep within the invisible ventilation shafts by perfectly applied microscopic layers of engineered aluminum tape. They might be completely invisible to us, but they really are the hidden heroes allowing our modern world to breathe. So keep questioning how things work, keep looking at the world around you with that structural curiosity, and we'll see you on the next explainer.